Hello, everyone. Super happy to be with you here today at Confer Conf. First of all, special thanks to the organizer who accepted me to this conference and allowed me to share a little bit of the knowledge that I have with you all. And my kudos to Rustam and the whole team behind ConferCon for allowing us to have this great conference. In this 40 minutes or so, we're gonna explore how we can move fast, build the things that we need to build, product, application, client service, whatever, in a safe manner. And we see the patterns that we can help us increase the agility, move fast, and deliver things faster while keeping the security and the safety of the data of our user and resiliency and safety and security of our system as one of the priorities as well. Before jumping into the fun part, a quick intro about me. I'm Mohammed. Um, I work in Spotify, a music streaming service. As a backend engineer, I am also a community guy and a Google developer expert for the cloud. So let's kick it off. We all know, and we probably all agree, that the demand for innovation and speed is everywhere. Users and clients and customers nowadays no longer wants to wait for weeks or even days to get their feature introduced, to get their bug fixed, to get the user experience improved. They want those things as soon as possible. In fact, they want them now. However, that enthusiasm for speed sometimes creates a conflict when it butts up with security, especially that security and traditional security tends to value status quo. And we end up by following that dodged hand to increase velocity by another type of risks and another type of challenges, such as skipped processes, inefficient testing, and especially um, security testing. And we all know, and we are all aware of a company that was bragging how fast they are moving, how fast they are shipping things, how fast they are introducing new features. However, as soon as um, security was noticed that is missing, the trust that he spent a lot of effort, a lot of money on was gone, then the users are not trusting the system, are not trusting the entity anymore. And I like to say that security is actually like air. When it's there, nobody notices it. But once it's gone missing, everyone screams. So have keeping the security of the users, keeping the data of the users safe. It's really important. So DevOps is definitely desired. DevOps, we allowed us to increase our velocity, ship things faster, improve the communication between the teams, especially the developers and the operations, allowing them to, once the artifacts are ready, ship them to the user as soon as possible. However, security is also required. Keeping the data of our users safe and sane is also important. So that's what DevSecOps actually tries to bring to the table. It tries to save the seat save a seat to everyone in the table. A seat for the developers, a seat for the operations, but also a seat for for security folks. And I hate the name, by the way, of DevSecOps. And as Solomon Hayek mentioned a while ago, that DevSecOps is just DevOps done right. We just need doesn't need to add any other part of to the name. It's going to get probably out of hand. But nevertheless, moving on. That's to say that DevSecOps, just to set a mutual understanding here, tries to save a seat to everyone in the table. It enabled the developers to build the things and do what they do best, to introduce new features, to improve the UX, to fix the bugs, to uh, apply what changes were required from customers and from the product and from different stakeholders. It enables the operations, though, to, once those artifacts are ready, once everything is green, ship those features and those patches as fast as possible to our production environment and make sure they are there. However, what DevSecOps tries and aims to do is basically make those artifacts, makes those releases more safe and secure, and make sure that nothing goes to production before it is certified and tested against at least the well-known vulnerabilities. And if there is a vulnerability, make sure that is patched and fix it before it goes to production. And so you're probably already aware of what this presentation is going to be about. It's going to be about the Formula One. During the pandemic, I had a lot of time to kill. I had a lot of time alone. Basically, um, locked in my house, trying to figure out the meaning of life. The war was collapsing outside, and yeah, you all know what's happening during those times. So I started watching the Formula One Drive to Survive Netflix documentary. Well, it's not a documentary, but it's kind of a series slash TV show slash reality show. But it basically tells the behind the scenes of the Formula One races, behind the scenes of what we don't see during the race weekends and the race days. In an entertaining way, sorry, in a very entertaining way, Netflix way. A lot of drama, a lot of things that keep you engaged, basically, and want to watch more. Nevertheless, I enjoyed it watching it for a couple of seasons, and then this actually happened in one of the episodes. Roma, who was part of the Haas team, was driving at a lightning speed, 300, more than 300 kilometers per hour, and that was during the Bahrain Grand Prix in 2020, so the year of the pandemic. And then he did a bad maneuver. Probably the car just didn't follow, and then he hit the barrier, and the car turned instantly into a fireball. And Roma stayed there in the fireball in the extreme heat for a couple of minutes. Now, by any measure, um, for the normal people, that is, such accident is severe. Such accident is almost a death sentence, except if a miracle happened. I was following also the during the episode the reaction of the Formula One people, the Formula One teams, the FIA personnel, basically the people that oversees the Formula One, and they were super worried, and they all thought that if Roman managed to get out alive from such accident is basically a miracle. And guess what? The miracle actually happened. Not only Roman managed to get out of such accident alive, but he managed to get out of such severe accident from the fireball, from the extreme heat, sane and safe on his own feet. And that basically got me thinking, what would happen if we started to design our systems and build our architecture with the same level of devotion as the Formula One teams design the cars? Not only focusing on speed, not only focusing on winning races, but also focusing on keeping the security of the driver a priority, which is really important. What I noticed while watching the episodes is that they mention or they keep talking about safety and they mention little security. And I am not a native English speaker, so I basically use the both word interchangeably. I use more security than safety. So I opened the dictionary and I found that security means the state of being free from danger or threat. And from a security engineering point of view and from a software engineering point of view, that is not what we are actually trying to achieve by applying the security measures. We know that from the moment we put our service facing the internet, we put our service accessible to the internet, there are hundred of things that can go wrong. There are hundred of thousands. Probably that's an exaggeration, but there are thousands of users that are trying to sneak into your system, break it, or at least use your system or what the node or the application as a base to attack other nodes and other systems. So this isn't right from a security point of view. This is not what we are trying to achieve. And when I looked up for safety, I found that safety means the condition of being free from being protected from danger, risk, from what to cause danger, risk, or injury. And that's what we're trying to do, right? We know that the system or the environment that we are deploying our application to is not safe. We know that there are a lot of malicious users out there, a lot of risky things, a lot of bad things that could happen, and we're trying to build layers, to build castles, to protect our application from whatever incident, whatever danger it is trying to break it to its knees. So good architectures should allow us, the developers, the DevOps team, the security team, to move as fast as we can in a safe and secure manner. We shouldn't try basically to block the system for security and delay its release, while we should not actually move as fast without worrying about security. We should find that balance. And that balance means that our architecture, our pipelines, um, our operations would enable us to do so. So I onboarded into a journey basically to understand the different regulations and the different patterns and the different rules that the Formula One folks follow in order to ensure the safety of the drivers no matter what happened. And there were a lot of regulations, basically, but I ended up shortlisting 10 important measures that they do and ensure 10 safety measures that they ensure that they apply to ensure the safety of the driver no matter what. And basically designing for the worst case, as we're going to see in a minute. And throughout this presentation, what I'm going to do, or I'm trying to do, is basically to go over those safety measures and check if there are any similarities, any patterns, any lessons learned that we can gain and apply in the software engineering industry. Basically, we're going to take the principles of the most dangerous sport in the world and try to apply it into software engineering and check if we can basically build and design our systems in a similar manner. And the numbers doesn't lie, the numbers don't lie basically. And here you can see that some graphs that proves that as we introduced more and more regulation, as the FIA basically, the entity that oversees the Formula One, introduced more and more safety measures, the number of deaths in the Formula One has decreased a lot. And this graph shows as well that as we introduced more and more regulations, more and more safety measures, the number of days between fatal accidents has also increased, which is important to ensure the safety of the drivers and ensure a safe and secure sport, because sport is about entertainment and keeping the driver safe and so on. So let's start. Those are the first five pre-crash measures, and we're gonna basically start to dig into them one by one. And the first one is the drivers in the Formula One have a seat belt, obviously, like a normal car, but the seat belt in the Formula One has a 6-point safety harness, and those 6-point safety harness has are basically built with multi-level of security, and they are tested thoroughly, basically to ensure that the safety of the driver is not at risk during a race weekend. The 6 point seatbelt is uniquely tailored for each driver to, yeah, to keep him safe, but also allow him to, depending on his weight, depending on his length, and so on and so forth. And it's also adjustable, basically to ensure that they are both comfortable and provided a high standard for safety for the driver. However, they are comfortable for sure, they provide safety for sure. However, the drivers cannot put them on his own. He needs the help of the driver of the pit crew, basically, to harness the seat belt. However, when he wants to release the seat belt, he basically press a button and it releases itself. And that is similar to push to deploy analogy in software engineering. And we can only achieve the push to deploy or push to production or whatever you want to call it only through automation. And automation has a lot of advantages, as you may probably know. Automation can enable teams to deliver greater value by eliminating manual efforts. And that is really important. It frees up to teams to follow other tasks, such as checking for vulnerabilities. Those vulnerabilities can, or those checks can be automatically handled. And those can free up the team in order to pursue more innovative tasks. Automation can also decrease the number of errors that occur with manual approaches. We as humans are sucks or are not good in manual tasks and manual work. So machines and automation exist in that. So delegating those parts to machines really helps in ensuring a more reliable system and a more reliable pipeline. And automation also creates more transparency in the end-to-end development life cycle process, which is important when the teams try to identify when or how or what certain action we're taking to fix a vulnerability, to fix a bug, to fix an incident. Uh, and from a security point of view, this is great to automate your pipeline project, your CI and CD projects. It can bring a lot of value to your team and your customers. The second thing they have is a stringent dynamic, static, and load test to ensure the safety of the drivers. They make sure to test the car in different conditions. They put the car in similar conditions, in similar environments that is going to run through in a race day. They test the car and the tires, obviously, for in a wet day, in a rainy day, in a humid day, um, and check how the car react, how the tires react, gather the data around it, and then try to improve the security and also try to improve the speed of the car. And in a from a software engineer perspective, there is similar to have a trusted, repeatable, and adversarial CI/CD pipeline. And what does that mean? Is creating a pipeline or a CI/CD pipeline that enable us to effectively and repeatedly test any change occurring to our application, not at one point in time, but throughout the life cycle of our application, throughout the different conditions or throughout the different changes that it has, and making sure that our application basically go through a stringent process to understand how it would react in certain condition, or to be more honest, on different conditions. And also, and more specifically, to ensure the security folks' involvement as we align through the process with increasing adoption of security practices. So, um, adversarial here means that while we're aligning on this ICD CI/CD pipeline and CI/CD process, we are having both inputs from the developers to that want to ship things faster, from operations that want to deploy things faster, but also from security that want to automate the security process and make it faster, and introduce security checks throughout the whole pipeline, and not leaving it until the end, basically, that is becomes a bottleneck and bothers the team. Another thing that we can apply, basically, to improve the security, to improve the resiliency and the checks, and making sure that we are testing our application throughout the same environment that is going to be deployed into, is canary deployment. And canary deployment is a pattern, basically, for rolling out releases to a subset of users and or service. And the idea here is basically to deploy the changes to a small subset of servers, to test it, and then roll the changes out to the rest of our servers when we are confident about the changes. So basically, we're deploying two versions of our application. The new changes to a small subset. We have automatic checks if you want an automatic threshold for a window of time, and then while you are confident the metrics looks good, there is we compare it to production traffic, and making sure that our new code is basically introducing no bugs, no regressions. And then once we are confident about it, after a certain amount of time, we'll roll it out to all users, and that help you to test your new changes, your new code, again in the same environment that is going to run through, which is basically production. Moving on, the third thing they have in the pre-crash measure is the cockpit is surrounded by deformable crash protection structures. And this is how the cockpit look like. They are designing basically for what we call in the software engineering, they are designing for failure. They have built the car around this structure, around this piece of structure, which sole purpose in existence is to protect the driver's life. And they are testing it all the time, and doing thorough testing to make sure that whatever the constraint, whatever the forces generate, how bad the crash is, basically can protect the driver's life and have minimal damage on the position of the driver, which is really important. And that is similar in our in software engineering, to design it for failures. And sorry, and designing for failure necessitates thinking about fault tolerance in all layers. No longer and application developers confine themselves to thinking about functionality only. We should design this functionality uh, in with the back of our mind on how we can provide this functionality with in the face of failure, in face of database outages, in face of network outages and crashes, in face of a lot of things that can go wrong, especially in a distributed system. Another thing we can basically have to ensure or design for failure is basically enabling and adopting MTLS into the different components and services that is communicating or circulate, or the communication, encrypting the circulation of the data and the information circulation in our cluster, but using MTLS. And MTLS is basically an extension of TLS. TLS is one way of connection, of one way of verification. MTLS, on the other hand, makes sure that both the client and the server must mutually prove they are trustworthy. And trust here is really important. And this is especially required in a distributed system with a significant share of what we call east-west traffic, where the client and the server are both services, and they are equal, and they're making both different requests to each other. So the idea here is to have no explicit trust, making sure that whoever we are communicating with is trustworthy, and enable MTLS helps to encrypt the traffic and the communication that is circulating inside our cluster, which is really great from a security point of view. Another thing we can adopt basically is designing our application in a micro-segmented way. And microsegmentation guarantees that sensitive systems are never exposed to the internet, which in simple words mean that we are putting the data and the on the systems or services owning the data as far away as possible from the internet facing system. So even if an attacker compromises an internet facing system, this structure deforms itself and try to protect the data of our users, and the user or the attacker will not have access to the final data, but they will have only access to the intermediate servers and services that not accessible to the sensitive data. And this is similar to a crash protected structure. You can compromise the outer layers of the car, or in this case the application, but you are not impacting the driver. You are impacting the most important thing that we have, in this case the data of our users. Moving on, time is running out for me, so I'm gonna be a little bit speedy in the upcoming slides. The third thing, or the fourth thing maybe they have, is that before they race, driver must demonstrate that they can get out of the car within 5 seconds. And drivers have to demonstrate that they can get out of the car within 5 seconds. This is effectively designed for the worst case, but this is not only designing for the worst case, but actually testing for the worst case. What happens if the car crashes? I want you to get from and there is a fire running, and I want you to get out of the car as fast as possible. Then you need to do that. Then show me when you have the perfect condition and there is no stress around. If you can't get out of the car within 5 seconds, in less than 5 seconds, goodbye. You cannot race for a day. And you do that every time before they get into, they step into the car or engage with the car in the track, which is really important from a safety and security point of view. And in software engineering, this is similar to what we call the chaos engineering principle, which is a discipline to identify failure before they became outages. By proactively testing a system and how it reacts and how it responds under stress, we can identify bugs and failures and fix them before they appear in the news, basically. And you have probably seen this map before. It basically tries to highlights the things that we know, and known knowns, unknown unknowns, and the unknown unknowns. And what scares me the most in the system that we design in the unknown unknowns. And by adopting chaos engineering, it helps to limit the amount of the unknown unknowns that we don't have. By intentionally breaking our system, we can gather more data about how it reacts in case of failure, and we can kind of build this mental model and mental exercise on how to react in case of incidents. So it's both important to build resilient system, but also from the on-call person on the your SRE to react in case of real incidents. So it's really important and a great win from different perspectives. And you can basically start small. You can start by forming hypotheses and designing the smallest experiment possible, and trying to understand how your system would react when something goes wrong. Um, and then take notes and analyze what went wrong and what went right, what went according to your expectation, and what was surprising for you, and then trying to design fixes and how to avoid such issues in the next time. And then once you gain confidence over one of the experiments, then you can grow the experiments gradually, which help you to build your confidence around the resiliency of your system. And the final thing they do in the pre-crash measures is the constant monitoring and replacement of the tires. Notice that they are not trying here to replace the tires or to patch them or to fix them. They are completely replacing them. And it takes around, this is the world record basically of replacing the tires, which is 1 second, 82 milliseconds. And now compare this and look how proud they are, how happy they are about replacing the tires completely. Compare this to the way we manage our services, our servers, and how happy that they are alive for a year or months, or it's to not say even years. This is to say that in the cloud native era and the rise of cloud, um, the pit versus cattle analogy gained a lot of popularity, meaning that we shouldn't give servers names, we should not lavish attention to them, we should basically treat them as cattle, which basically we spin them up as well and then throw them or kill them when we and throw them away when we don't need them. So if we accept this zoomorphic analogy, what would happen if we add another concept here, which was the chickens? Chickens obviously grow to maturity much faster than the cattle. 6 weeks compared to around 24 months for the cattle, and the amount of resources that you need to grow up a chicken to maturity is orders of magnitude less than the cattle. That's to say that there are other metrics basically that we can introduce in order to help from a security point of view our systems. And the first one is reverse uptime. And to explain it, I'm probably start with an example. So imagine that you have configured and secured a production cluster, and in that cluster you are running a mission critical services and application. Now a hacker managed to find a security hole on your software stack and has gained root access basically to one of your cluster nodes. That alone and that by itself is bad enough. But even worse, the attacker managed to hide his presence. User didn't know that he gained access to as a node or as a base to access and to attack other clusters and other nodes, probably in your inside your cluster or outside your cluster. So now what would happen if we just kill each cluster node after a certain uptime? Let's say 1 day. Once the node is out of the cluster, it is torn down and replaced and freshly provisioned by a new node. That way, the hacker has lost their base and the problem has been resolved, at least temporarily. And the attacker would need to redo the same process again in order to gain access to your cluster. So, from a security point of view, this is a great win because you can't backdoor a system that is constantly being revised, um, which is really important, especially in the distributed systems. And it's probably easier nowadays than before in the age of containers and the cloud. Now, combine this with the base image freshness. And the base image freshness is basically the base image that you use as a base layer to build upon the different images that you deploy your applications on. So, tracking the base image freshness means what was the last time that basically you updated your golden image, that you patched it for vulnerabilities present in your base image. And that if I'm a security engineer and I patched my golden image and patched my golden image for, let's say, a 0 day vulnerability, I know that the maximum amount of time that, and I have reverse uptime of course, I know that the maximum amount of time because my before my base or patched base image is rolled out to hold my cluster is basically the reverse uptime, which is really great from a security point of view. Combining those both approaches, you don't need to do um, uh, a stress day of patching all the images. By combining those processes, you already have a process that's basically continuously and constantly patching and fixing security vulnerabilities in your cluster, which is great from a security point of view. So those were the five pre-crash measures. Now let's dive into the five post-crash measures, starting with driver can be extricated from the car by lifting out the entire seat. Now, in our cars, when a car happen, you can't lift out the seat. You need to open the door and break the car basically to get out the driver if he, in case he passed out. Um, in the Formula One cars, if the driver passes out and the rescue team can't get out the driver from the car or he can't get out from himself, they can lift out the seat, the entire seat from the car, put it somewhere and try to save the driver's life, um, which is really important. So the the design of the car in a modular way enable them to extract it completely in case extract the seat completely in case they needed to. And from a software engineering perspective, this is similar to having a loosely coupled system. Um, uh, Designing our system in a modular way will help us to react in terms of issues, how fast you can change your certificate that has been leaked to internet, change a password that was has been unintentionally leaked, how fast you can react to whatever, or an SSH key that was unintentionally published to GitHub or whatever your a public repository is. So how fast you can react to those security threat, it's really important. And couple system help you to react to those changes faster. And we all know that there are already a number of benefits of loosely coupled system. There are fewer dependencies. When you want to change something or you change it, you don't need to update a lot of dependencies. You just update the system that you own without affecting the other dependencies, which is already great. And that way you can isolate failures. You can design your system. If one of those components failed, that doesn't mean the whole application or the whole or the whole system would fail. Basically only one functionality, which is the service or the this component is responsible of, is inaccessible, and not the whole application. And having a loosely coupled system enable you to ensure evolvability of your architecture. You start with the smallest possible MVP, minimum valuable product, basically, and you can grow it and evolve it as you know better about your product, know better about the market, know better about the requirement, rather than designing this rocket ship when and have a lot of issues to improve it afterwards. The other thing they have also, they have a hands or a hand system, and hands stand for hands and or head and neck system, sorry, that basically absorbs and redistributes forces that would otherwise hit the driver's skull and neck muscles. So the hands is basically this small little black thing here, and basically when the forces generated by the crash is massive, so the hand system basically take those forces and redistribute them to the driver's body, that otherwise would hurt his skull and neck muscles. And this is similar to adopting some of elasticity and building elastic architecture. If you're having a good day and a lot of traffic is coming, have a load balancer that distributes traffic evenly across your node. If you're having a very good day and your existing node couldn't keep up with the load, then having an auto scaling that spin up other nodes to handle the node is important. Having a request time threshold to free up the CPU and the resources in case of one service is starting to act slowly. In some cases, having a degrading performance is better than having an outage. And also adopting some anti-overload pattern helps you to overcome some bad days and increase the resiliency of your system, such as circuit breaking and exponential backoff. The other thing they have with driver suits are fire resistance, and the driver suit keeps the driver body under 41 degrees Celsius for a few seconds, which is really important. And this is This is how our driver Roma, our friend Roma, managed to get out of the car because, like, the suit was containing him, even it was inside the extreme heat. The suit managed or managed that to keep his body and under 40 degrees. And it's similar to building layers of defense in our application and keeping our data in as much as we can, starting with adopting the least privilege principle by giving our application the minimum access right and resources for it to perform its function. Also, adopting defense in depth and building a series of defensive mechanisms that are layered in order to protect valuable data and information is also important. And adopting zero trust policy and by eliminating implicit trust and continuously validating every stage of interaction. Um, so those patterns, trying to adopt them, are really important to try to keeping the data of the users and the system is safe and locked in. Another thing we can have is hardware security modules. And hardware security modules, you can have them both on your private cloud or they're available in all public clouds as well. And to understand what hardware security module does, let's take an example. So let's imagine an attacker accessed and extrapolated the content of your database, and he managed to get out or copy the database outside. The database contains a table where you have the passwords. You manage to brute force the password and manage to crack it and understand or get a copy of the your user's password, and you won't know about it unless you found it in the black market. So let's imagine the same attack, but instead of having to encrypt the password use or hash the password using a function, you would require basically a key each time you want to hash your password. And if you want to compare the password, what you would need basically is each time you want a key to compare the passwords, you would require a key from the hardware security module. Adding this extra step makes the content of the database, uh, even if the attacker managed to get in it, it basically useless because he can't recompute the password and crack them without the hardware security module. So you are trying to keep in the attacker in your system until you are aware and your alert system basically are aware of it and trigger alerts and kick him out and fix whatever vulnerability he used to get inside. The other thing they have is a fire suppression system that can be activated by the drivers externally or by the race marshal. And look how they distributed basically the 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 authority and the access depending on the situation. If the driver is awake and there is and there is a fire, the driver can basically trigger the system. If the driver passes out and the rescue team arrive to the crash scene, they can trigger it by pressing a button outside of the car. If the driver's passed out, the rescue team cannot get hold of the car, then the race marshal can basically trigger it remotely. And there are many in the software engineer system ways in how you distribute access. Um, Having communication policies is really important, since it enable you to define kind of virtual boundaries and virtual realms of your application, and be aware of not being too optimistic about it and giving access to too much people, and avoid looking yourself out and leaving the key inside. So having a balance is really important here. And finally, Formula One are crazy about data. They have data about everything. And needless to say, that no system should go to production without having monitoring tools in place and alerting tools in place, especially security alerts that observe or detect unusual behavior and trigger alerts. Um, This is how the Formula One or the Formula One drivers sit inside the car. It is definitely not comfortable, but is a matter of balance and a matter of trade-off between speed and security. This allowed them from an aerodynamic point of view to gain the maximum and extract the maximum out of the car and improve its speed. But it also, as we saw before with the cockpit, enable them to ensure their security. So it's a matter of balance, and that's something you need to keep in mind while designing your application and architecture, and find the balance and the trade-off between speed, or increasing velocity, and also the security. And I want to end this presentation with this scary number from the cost of data breach, and they found that last year the average business cost of cyber attack was a little bit less than 4 million. But the second number scares me the most. It takes over 270 days to detect a data breach, which is a long period of time. So I hope throughout this presentation you have some concepts, not some patterns that you can adopt in order to increase the safety of our architecture, of our system, while keeping or even increasing the velocity of our system and how we ship things. Thank you. If you have any questions afterward, please feel free to ask them. I'll try to answer them in the Slack or in the chat. And you can reach out to me in my Twitter, and my Twitter handle is Laytoon. Those are some resources that helped me to build this application. Thank you all. And again, thank you to the organizers for allowing me to be here. And see you all. Bye.